In this video, we're going to look at a specific type of surface called an ellipsoid. The sphere is actually one type of ellipsoid. And so let's suppose that we have the general equation where a, b, c, and d are real numbers, and we have ax squared plus bx squared plus cz squared equals d. I'm going to enter this into Calcplot 3D using a, b, and c as parameters, and I'm going to let d equal to 1. So the only thing I'm going to change here, it doesn't have to be 1, but I'm going to put a 1 for d here, and then we're going to take a look at what kind of object we obtain as we change the values of a, b, and c. So below is the Calcplot 3D web address if you would like to use it, and I'm going to enter this equation as an implicit equation. So if we look below at, one second, let me scroll a bit up. This is the Calcplot 3D application, and I'm going to go to the Add to Graph on the left, the tab on the left, I'm going to select an implicit equation. So you can see we get a big list, implicit surface. And into the equation, I'm going to put in ax squared. Oops, of course I messed that up. Let's see, ax squared plus by squared. Nope. Plus cz squared, and I'm going to set that equal to 1, and I'll press return so we can see what we get. So notice first that on the left, this application has created sliders for A and for B and for C. Right now each of these is set equal to 1, and we get a sphere of radius 1. So let's talk about that for a moment, and then we'll try to play around with different values of A, B, and C. So our first example will be x squared plus y squared plus z squared is equal to 1, which is what we get when A, B, and C are equal to 1. And this is a sphere of radius 1. We've seen spheres before, but I want to show you how we can use the traces to make sense of this graph. So if we consider, for example, the xy trace, that means how does our surface intersect the xy plane? So we set z equal to 0, and with quadric surfaces, the traces are conic sections. When z is 0 here, we get that x squared plus y squared is equal to 1. That is a circle of radius 1. If we take a look at the xz trace when y is 0, we'll have that x squared plus z squared is equal to 1, another circle of radius 1. So the first one on the xy plane, we're getting a circle of radius 1. Oops. Okay, I'm not used to this application as much as I am to some of my other ones. So circle of radius 1 on the xy plane. On the xz plane, the intersection of the surface and the plane is also a circle of radius 1. And the same thing happens on the yz plane. So the yz trace, when x is 0, we're going to get y squared plus z squared is equal to 1, so another circle of radius 1. So this sphere has, each of its traces is a circle. If we go back to the Calcplot 3D application, I'm going to move around a little bit the graph so that you can see how we're seeing the traces. So if I look, for example, from the perspective of the YZ plane, you can see that the intersection is a circle, right? There's our circle of radius 1. And you can do that for any perspective that you take above one of the coordinate planes. So that's how we can use traces to make sense of the graph of the sphere. A sphere is a type of ellipsoid. So let's see what happens if we adjust our parameters A, B, and C. I'm going to let B and C equal to 1. I'm going to leave them at 1, and I'm going to change the value of A. So if I increase it a little bit, notice what happens. If we increase the value of A to 2, we have flattened this sphere along X. It gets thinner. And if we make the value of A become smaller, but still positive, wait a minute, still positive, we get an ellipsoid where along the x-axis we have elongated. So that's important, right? As the value of A gets bigger than 1, along the x-axis this becomes narrower, and less than 1, but still positive, it becomes elongated. Let's talk about why that happens. So if we, for example, let's do this one in a different color. Let's suppose that our value of A is 2. So we have a 2x squared. We're going to leave the coefficient of y squared as 1 and the coefficient of z squared as 1 and still have d equal to 1. Well, this can be thought of as x squared over 1/2, because dividing by half is the same thing as multiplying by 2, plus y squared plus z squared equals to 1. And if we now examine the xy trace, when z is 0, we're going to get x squared over 1/2 plus y squared over 1 equals 1. And this is an ellipse. So another conic section where half of the length of the minor axis in this case is the square root of 1/2. So that's why it gets very narrow. If we consider the trace along the x-axis, along y we still have intercepts of 1 and -1, but along x we'll have the square root of 1/2 and negative root 1/2, which are smaller than 1, and so we get an elongated ellipse along y, but along the x it's become more narrow. And you can do the same if you let the value of A be smaller than 1 but still positive. Let's try another example for that. And we could do the same thing for B and C and predict what would happen to the graph. So I want you to think about that, what might happen to the graph if we alter the values of B and C. But as another example, let's suppose that we have x squared over 4, so that here the value of A is the value of A in our graph is 1/4. Our parameter is 1/4, so smaller than 1 but still positive, and we'll leave B and C also as 1. So this is our equation. If we consider, so when we looked at the CalPlot 3D application, this became more elongated along the x-axis, and it was an ellipsoid. And the reason for that is that if we look again at the xy trace, we have an ellipse, which is x squared over 4 plus y squared over 1 is equal to 1. But this ellipse, the intercepts along the x-axis have increased from before, so that they're the square root of the denominator. So that becomes a 2 and a -2, and then y is still between -1 and 1. And so you can see why this becomes elongated in the direction of x. So I would encourage you to play around a little bit with the values of B and C. I'll do it here, but won't consider the traces independently. But if I take A and leave it at 1, so I'm going to adjust it so I keep A at 1, and let B get larger, you can see that this is getting narrower along the y-axis, but when B gets smaller but still positive, it gets elongated along the y-axis for the same reasons that we discussed in the other examples. And I can do the same thing with Z. I can make it shorter along the z-axis or longer along the z-axis, before we become negative, and we elongate the ellipsoid along z. In the next video, we're going to talk about what happens when one of these parameters is negative, or maybe when two of the parameters are negative, and that will result in hyperboloids.